Our next speaker is coming from the north, and her name is Tarah Young. She's an extension educator with the University of Minnesota out of the Park Rapids, Hubbard County area. So welcome.
Good afternoon, everyone. Hi, my name is Tarah Young, and I'm an extension educator up in Hubbard County, up in the north, as Bruce said, up in Park Rapids area. And kind of to get over the afternoon slump, let's talk about everyone's favorite topic, small grains. They're short like me, so I think it's a fitting research topic for me. So I just recently finished my Master's of Science in Applied Plant Science this past June, now working full-time for Extension. And I worked with Dr. Dan Kaiser, the nutrient management specialist, and Dr. Joachim Wiersma up in Crookston, which is even further north than I am, the small grain specialist. And we're really focusing on the nitrogen management for hybrid rye as a grain and a forage crop in Minnesota. So this is the crop of interest that we're working with. And winter rye in general is just a remarkable crop. I really didn't have any experience with it before conducting this research. But hybrid rye in particular is incredibly amazing. So it has a shorter pollination window. It has a lower risk of ergot. So that means it's a more uniform pollination and with more pollen. It has 2 to 4 times the amount of tillers, and which contributes to the higher yields, the higher returns. And there was a recent study that was published just a few years ago that found that if a producer made the switch from an open pollinated winter rye variety to a hybrid rye variety, there was a 94% chance increase in net returns. So this has a very high potential for a new and emerging crop in Minnesota. So when we look at just these variety trials that Dr. Wiersma had conducted the last 3 years, we're seeing in the yield differences between hybrid and open pollinated varieties, significant differences. The red bars here are the hybrid varieties, and the gold are the open pollinated. So the mean yields that are labeled with the same letter are not significantly different at an alpha level of 0.1. And we're seeing a 30 to 40% yield difference between even the best performing open pollinated varieties versus hybrid rye. So because of these higher yields, it kind of begged the research question, does hybrid rye have higher nutrient or specifically nitrogen recommendations? So as we dug into this question a little bit more, we found there was there was not a lot of data. It was very limited, focusing on just the N application of these hybrid rye varieties specifically. So when we looked back at the previous recommendations, for the university, they really only centered around open pollinated varieties. So the only information that came from industry, or specifically on hybrid rye, came from industry, and we're seeing about 144 pounds it was a yield goal based determination for nitrogen. So for about 120 bushels, they were estimating a required amount of about 144 pounds of nitrogen. But that really doesn't tell us when these applications should be made. It tells us the total amount. So we really saw a lot of restrictions and limitations when it came to the previous recommendations. So we're seeing that the new recommendations were needed, and as far as rate and as well as timing of when to apply. So there were things that were a little murky, but what did we know is we had to take a step back. So in nitrogen management in small grains, nitrogen is often the most limiting nutrient, leading to decreased grain yield, grain protein and content, and biomass production. So this graph here shows the pink curve is the yield curve, and the blue is the protein. And we can kind of see how the yield starts to plateau and even maybe decrease a little bit while the protein still continues to increase. So we know that optimizing nitrogen applications are definitely important for both the yield and the protein concentrations. Then on the flip side, we can see excess nitrogen can also increase lodging, as you'll see in my research. You'll see that happen a little bit, as well as disease just with the increased biomass, less airflow in the stand. So we definitely want to have that optimal rate as far as application. And now timing is also very important when we look at nitrogen management, because applications of nitrogen basically up to mid-stem elongation really contributes to the yield and usually has a really little effect on protein, while the later applications would have more impact on the protein concentration and not so much on the yield. So in the winter rye cereal, there's really several opportunities as far as timing for these applications. So we look at planting, which is usually in September, usually for most parts of the state. Can be October in the southern parts, but looking at a pre-plant nitrogen application, so whether that's incorporated before planting or broadcasting right after planting. There's also an opportunity to apply nitrogen in the late fall, usually around that November timeframe, going into winter before a freeze up. Early spring, and I do have to emphasize early because rye is particularly an early grower. I've seen green up as it was like 31 degrees, and it's starting to grow right away in the fall or in the spring. So I emphasize early spring for the third opportunity for an N application. And then we would harvest for grain in the summer around that August timeframe. So we have 3 opportunities for nitrogen applications. So really what our research question was, how much nitrogen should be applied at planting in the late fall and in the spring to maximize or optimize yield? So there was a lot we didn't know, which is why a lot of rye producers have had many questions. So questions such as, does hybrid rye have higher nutrient input requirements? How much nitrogen should be applied in the fall versus the spring? What is that optimal split to maximize yield? In areas where the soils might hold on to a little bit more water, or if we have for these very intense precipitation events, my fields are too wet in the spring. Can I get it? I won't be able to get it out there early enough for the rye to actually utilize it. So can I apply it on in the fall, in the late fall, and then just hope that it stays there for the rye to use it in the spring? We also had a component, I'll be talking about this, but not super in depth, but more on the rye silage on the forage component side of things, comparing it with the corn silage, return on investment. And additionally, does the addition of rye in my rotation help reduce any nitrate losses? So all of these questions that we were communicating with rye producers about, these really directed the research objectives. So out of my research, the first objective is to establish nitrogen guidelines for hybrid rye. What is that optimal split, that fall or pre-planting fall, spring split? Evaluate the use of commercial nitrogen extenders and additive products. I know several speakers have been talking about that. Different strategies to utilize to be able to place that nitrogen and to be able for the rye to actually utilize it when it needs it the most. Assess soil nitrogen or nitrate concentrations in hybrid rye and comparing it with the corn system, and then also comparing the yield and forage quality between the two systems. So we conducted this research all over the state, and we had 6 locations, 2 up in the north, 4 in the southern half of the state, with Becker also being on the irrigated sands. So that kind of made it a little bit different across varying geographies, zones, and soil textures. So objective 1, we designed a nitrogen rate and timing trial, which comprised of 5 pre-plant nitrogen treatments of 0, 30, 60, 90, 120 pounds of nitrogen applied pre-plant and then incorporated. And then spring treatments of urea as well, from 0 to 150 pounds in the spring as early as possible that I was able to get out there. So, so to achieve this first objective, we had this trial, and we wanted to identify the optimal split. So it was those 6 locations over the 2 years. We also had 4 additional sites the 3rd year of the trial. So to go into the results a little bit, so these are the 3 years, the 2022 through 2024. And the highlighted boxes show the site years where the different rates significantly impacted grain yield in hybrid rye. So we're seeing pre-plant nitrogen. There were significant differences between those ppn rates in 3 of the 16 site years. In the spring, there was 11. That's these yellow boxes. There was 11 out of the 16, and there were significant interactions in 2 out of the 16. So that kind of tells us that spring N is more important than the pre-plant nitrogen, but not exclusively, as I'll dive into a little bit later. So when we looked across relative yield, this is I took out the yield or I made it relative yield because then I could look at across locations. So basically, in the north there were generally higher yields than anything in the southern. So this made it all across all the locations. So when we looked at within pre-plant nitrogen rates, we can always see the spring, which are the maroon bars, are always lower, regardless of which pre-plant nitrogen rate group that they were in. Definitely significant differences between the pre-plant nitrogen 0 pounds. So I used that relative yield to take out like that site year effect, so we could just look at what the pre-plant nitrogen rates were doing. So when we did the flip side, then I looked within the spring, and it basically told us the same story, how spring zeros were very significantly different, but looking at the higher amounts of spring, we're really not seeing a big difference between the pre-plant nitrogen rates. Even at the zeros, for the majority of the spring rates, pre-plant nitrogen was not nearly as important. So if that wasn't enough to basically solidify that, hey, spring nitrogen is pretty important, I also conducted different regressions. So this was just kind of another confirmation that it told us where are those optimal rates. So I did quadratic and linear regressions. All that means is that quadratic was generally on the more conservative side. It basically gave us a range between linear and quadratic. So we can see my R-squareds are very, very low. If you want to see the messy data, I suggest it would probably give you a headache, but it is small grain data is very, very messy, but this was a nice pretty graph to show based on the averages. But we're seeing between 65 and 82 pounds ideally at the rate within the group of 0 pre-plant nitrogen. So any more N than this would basically not significantly increase yield. So we're seeing 60 to a 90, I would conservatively say. And that's also why we analyze the data in multiple points, is to see the big picture, to tell the whole story. So then when I looked at just within the pre-plant nitrogen group of 30 pounds per acre, it definitely shifted. So between 39 and 58 between the two regression analyses. So the optimal rate definitely shifted lower the more that we have the pre-plant nitrogen. But then when I looked at the pre-plant nitrogen, because we're kind of seeing that 60 to 90 range is ideal. I kind of wanted to do the reverse to make sure, kind of to cross-check. So we're kind of seeing that 15 to 20. So about 15 to 20 pounds in the fall with 60 to 90 in the summer or in the spring. So that's kind of what we're seeing. It's a lot of different ways of looking at the same thing. And I wanted to look at it a third way. So I looked at these different combinations. And because it was really messy data, it was a little difficult to tell differences between all of these combinations. We're seeing that rye can definitely utilize not as much nitrogen as we were anticipating, so it can still significantly yield. You can see all of these are part of the same highest yielding group. So one of the ways was to evaluate these combinations was to narrow in a little bit by going to the net return. So I calculated the cost of nitrogen in the fall versus like a 10% increase in the spring. So if there was any differences there, and also utilizing a $6 per bushel rye to kind of try to parse out these differences in net return. And here it helped a little bit, but what we're really seeing is kind of the two winners that float to the top are no pre-plant nitrogen and 90 pounds in the spring, and 30 pounds of pre-plant nitrogen and 60 pounds in the spring. That's kind of what we're seeing when we start looking at this, because the main goal of these nitrogen recommendations were to find the optimal rate that maximizes and optimizes production, economics, and environmental sustainability. So it's kind of trying to think of these in a tri-dimensional aspect. So a lot of these, or between these two, it's the same total N, but really the timing could depend on location, as I'll talk about here in the next slide. It's the soil type, the residual N, the cropping history, the precipitation can all have an impact of which one we would probably go with. So looking at the regional differences, so the southern, and I'll blow up each one of these, so if you can't see this, that's fine. So the southern, definitely, there was less differences between all the nitrogen scenarios. Northern, there was definitely more stratification that we like to see, a little bit differences between, the zero, the control, and any of the rates. And then as well as the irrigation. So we were able to see that, of course, kind of as we had hypothesized, that the pre-plant nitrogen really wasn't able to be stick around long enough for the rye to use it in the spring. But irrigation definitely seemed to prefer the spring application. So as we go into the regions, so the southern, I'd like to draw your attention to avoiding these 4 lowest treatments. Basically spring in is definitely important, so we don't want to leave it out. Any of these very, very low, I did kick out a lot of those, the 120 pound, 150 pounds, just because it wasn't necessary, so we could really focus in on these lower rates and try to make distinctions. And going in between these two, there really isn't a big difference in these southern locations between the 30 and 60 and 0 and 90, still the same total N. But we're wondering if the residual N, maybe in these southern, that these plots did definitely have a high residual N in our preliminary soil test. So maybe that was that little bit of nitrogen that was hanging around still was enough to basically get that rye to basically take off, some tillering to happen, and then basically give it another shot of nitrogen in the spring. So here I something kind of like a flag treatment that I always like to see among all these different regions was to look at a higher pre-plant nitrogen rate and a 0 spring rate to kind of see how well that nitrogen, that urea specifically, stuck around for the rye to use it in the spring. And it is still in the highest, barely in the highest yielding group. So definitely what we're seeing is hybrid rye really has much lower nitrogen rates than we expected, but we still do need to have sufficient pre-plant nitrogen and spring, or a sufficient spring and very ideally very early application in the spring. So when we look at the nitrogen, we're seeing much more stratification. When we look at all of these lower, we probably want to avoid all of the ones that don't provide enough spring. And maybe in the northern, it's definitely the fall nitrogen was not cutting it. So we definitely needed to prioritize the spring nitrogen. So this one was a little bit more obvious. It was still, there's still very significantly there's a lot of the yield treatments were very similar, but the pre-plant nitrogen was more important in the northern across site years. So when we also look at the zero spring, but the pre-plant nitrogen, like I was kind of saying, that flag treatment, it definitely was part of the lower yielding treatment. So definitely spring is very important also in the northern. And irrigated, and this one is just the Becker location. So when we look at the 0 and the 60 and the 0, we're really seeing those lower yields. We're really not able to carry over that pre-plant nitrogen into the spring to be able for grain fill, and we definitely want to prioritize. Oh, why did that move? Oh, my little thing stopped moving, maybe. Oh, it's not responding. I just won't touch it. So what we're looking at, we're really trying to prioritize across, there we go, really trying to prioritize across all of the regions, spring N, and a very similar story. But we don't want to have excessive nitrogen, and this is kind of what I was referring to, the lodging. In 2022, Becker had a significant lodging problem, and this is the example of why more is not always better. So basically in this graph, the lower the lodging rating, it's not very intuitive, but the lower the rating, the higher the lodging. So we can definitely see more and more lodging, even with just 30 pounds of N. So we should be very cognizant that small grains can be very sensitive to over application of N. But another factor to consider is the weather. We've been talking about weather a lot today. And this, of course, is just another confounding factor because these are the same rates. Hopefully you can see this well enough. But basically, this is the raw data from Becker 2022 and Becker 2023. 2023 had the really beautiful, nice yield curve that we like to see that plateaus out. But Becker 2022 had the lodging problem, and you can see almost a linear negative relationship between, and this is, I mean, the highest yielding was 0 pounds of nitrogen, just because any additional nitrogen contributed to a increase in lodging. So not that the grain wasn't there, it just wasn't able to be harvested. So, and then when I looked back at the weather data, 2022 had a very cool, long, extended spring. It produced a lot more biomass going out there. It was quite tall even before it started lodging. And then as opposed to 2023, we had a very quick, I don't even think you could consider it a spring. It was just all of a sudden hot, dry. I went out there and it was Becker, so it should have been irrigated. I went out there and I was like, is this even being watered? It's so dry looking, definitely a lot less biomass. And we know that with small grains, heat and drought effects can definitely affect the plant height, the stature of the plant, but usually doesn't significantly impact yield, which is nice for a small grain to kind of compensate for that stressor. So definitely very interesting to talk about the same nitrogen treatments, but weather is a very different compounding factor. So a few conclusions for objective 1. This obviously, as I was saying, the spring applications are much more important than the fall pre-plant nitrogen applications. In the case of Becker in 2022, the excess N can also decrease the N efficiency and also increase harvest losses, but not all of the time. So the recommended N application across sites, across the states, is a very small, less than 30 pounds of nitrogen. Starter N applications usually can be combined with the MAP or DAP applications that are contributing small amounts of nitrogen, as well as a 60 to 90 pounds of nitrogen in the spring. In contrast to the 140 pounds of nitrogen that some of the industry folks were talking about. So objective 2, a lot of the previous speakers were talking about N sources, so I probably don't need to go into full detail about what these different sources, how they contribute and how they extend the nitrogen transformation process. But what we were looking at was, can we utilize these products can we utilize them in the late fall so we can delay or eliminate the spring application? There's a lot of things going on in the spring, so is that one thing that we can kind of check off the plate, say the rye is, we're good to go? Can we kind of front load that? So we used agrotine, or urease inhibitor, ESN, so for volatilization, and instinct for nitrification inhibitors, and then super U, which is a combination of the two. So because we know that rye is a super early grower, it resumes growth right away in the spring. So can we strategically use these different products to allow rye to access these right away? Like, it was easy for me to go out and hand apply this fertilizer because I was able to just go out in my muck boots, but that might not be as plausible for farmers to get out there with big equipment. So can we use these sources? So we used the source and timing trials. And this time we actually had 3 different factors. So we had a pre-plant 0 and 30 pounds of nitrogen. And then we also had the source timing. So that was in the late fall or early spring. And then we also did those 5 different sources, and as well as a no nitrogen control. So all of the source rates were at a 60 pounds of nitrogen, and then applied either in the late fall in November or very early spring in April. And these were in like 5 of the locations over the 2 of the years. So here we can see the results, that there was no significant interactions. And we're really only seeing, for the pre-plant nitrogen, we're only seeing in 2023, 2 of the locations where the 30 pounds of nitrogen yielded more than the 0 pounds. So only 2 out of the whole 9 site years that we analyzed. And then this one, Rosemount in 2022, the late fall actually yielded 12% lower than the spring did. But that was only 1 out of the 9 different site years. So that's why we were kind of saying, in general, there was no significant difference between late fall and spring. It was very, very close to being on the line of statistically significant too. So, and then looking at the sources, the yellow boxes, 4 out of the 9 site years were significant, which is what we would expect because we had a 0 nitrogen control. So that's what we were expecting to see. So here I parsed out between the fall application and spring application, and here we can see definitely the no nitrogen control. There's a clear end response, but not a huge difference between the different sources within fall or the spring across the different sites. So this is really consistent with the rate trial results, basically that zero nitrogen yielded less than something with 60 pounds of nitrogen, but there was really no disseminating differences between the sources for these 2 research years that we had conducted. So no difference between the late fall and early spring applications in these 2 scenarios, or in the 2 site years, or in the 2 years. So this hopefully can contribute to the increased flexibility with this late fall and application, but we still want to be very careful when broadcasting urea in the late fall. So it can be extremely weather dependent, where the soil temperature is under 50 degrees ideally, so we're decreasing the chance of nitrification, and to really slow that nitrification process, and precipitation, as Fabian had talked about. Maybe usually our recommendations are hopefully to get 1/4 of an inch of rain, but it might be over like 3/10 of an inch. It might be a little bit more substantial depending on those, depending on the current soil moisture and the temperature. So definitely field site dependent, where it's soil type, and the slopes to be also cognizant of too. So precipitation, because we really can't incorporate after the hybrid rye is growing. So we're a little limited there, but it does seem to be that a late fall is very consistent with an early spring application. Objective 3, so assess soil nitrate concentrations in hybrid rye and corn. So we hypothesized that rye utilizes more moisture, and along with it, we would conclude nitrate, better than corn in the spring and the fall. So this graph, we can see kind of the red line is the corn nitrogen use, basically like the highest nitrogen use, basically in the early or in the middle of the summer, whereas the rainfall pattern and thus the hybrid rye growth really mirrors that the leaching and runoff potential because it's growing in the late fall, in the early spring. So that's what where our hypothesis was. And if I have learned anything about research, it is that things almost never go to plan, and this is no exception because 2022 and 2023, you probably don't need to be reminded, were very dry years. So when we installed these lysimeters, basically to collect water in these rye and corn plots, yeah, when I went to go out and use this pump to go out and extract these samples, you probably wouldn't be surprised, but there was no water in the rye, especially. And we installed the lysimeters in a 2-foot depth in the rye and the corn plots. And the rye plots were dry as a bone for the majority of the time. The corn, right after a precipitation event, or if it was irrigated, like in the case of Becker, I was able to really gather a ton of water, especially like up until like that B10, B12, depending on the precipitation. But so that kind of like very anecdotally, it tells that, okay, if there's no water in the soil profile of the hybrid rye plots, there's also no nitrate leaching. So anecdotally, it is very cool. I don't have the data to go along with that, but I tout that as a really interesting observation in this study. The one thing I was able to calculate, though, was the nitrogen uptake efficiency. Because I was able to use the above ground biomass because we took silage samples between the rye and the corn silage. So I was able to compare basically the applied amounts versus what was in the above ground biomass. So I basically back calculated the protein, extracted the nitrogen out of that basically, and then also the silage yield, and then was able to basically compare the N rates between all of these. So the left graph here are the 2022 sites. The right is the 2023. So basically, there we go. So basically, 100% in this graph, are these red lines, means that the plants retrieved 100% of the applied N. So above those lines, the rye really scavenged all the N that was not applied in these trials because we're seeing, 300 to even 500% retrieval rates. So below these lines, it doesn't mean that they didn't utilize it in the above ground biomass. It just means that it just wasn't in those samples. So it could have been in roots, definitely. So this wasn't really a concrete way of saying this is how much nitrogen it can uptake. It was a really great way to compare the nitrogen efficiency among the different sites. And not surprisingly, we see Becker definitely has like the lowest nitrogen use efficiency. But even so, look at Becker in 2022, 300% retrieval rates, and then in 2023, 200%, even at just at the 30 pounds of applied N. So it's really an effective scavenger of nitrogen and of water. So that was about the only thing I was able to actually get data from. But very anecdotally, it was very interesting to observe with the water part. So the final, I don't want to cut into Anna's talk. So this one I won't be going in as much depth, but I'll be around if anyone's interested. But the fourth objective was to compare the corn and the rye silage systems as far as economics, the inputs, as well as the quality impact or the impact of nitrogen on these different quality indicators. We had 6 different site years for corn, and we looked at grain yield, grain protein, silage yield, silage protein, and silage total digestible nutrients, and also looked at that in rye. And what we found here is just kind of the ideal. I did a similar linear regression, linear plateau regression, and just as Jeff was talking about, where we're seeing lower nitrogen required rate for corn silage. So that's kind of the basis that we took, was that corn in this study needed about 200 pounds of nitrogen to optimize its silage potential. So when we compare the tonnage, the silage tonnage between corn in the yellow and hybrid rye in the maroon, corn always will outcompete rye in terms of silage tonnage. I think it's just inevitable. But when we looked at the protein, and not shown here, the protein was always higher and in the hybrid rye. So then when I also looked at the total digestible nutrients, and that was a toss-up between half the times. So 3 out of the 6 site years, the hybrid rye had a higher TDN. 3 out of the 6, the corn had higher TDN. So there were definitely gives and takes. So when I was doing the economic analysis, I had to look at everything, hopefully more as a system view. So we could see a less nitrogen input that for the rye compared to corn, so over 2 times as much N, instead of 60 to 90 pounds of nitrogen as needed for the hybrid rye, we needed about 200 for the corn silage. And then we also have the value of the forage quality. So I kind of did like a simulation of 3 different scenarios. So if we had the same quality hybrid rye to corn, higher corn silage quality versus higher rye silage quality. And when I did the net return comparison per acre, really the only scenario that really the net return was similar was if hybrid rye had the same or had higher quality than corn silage. So, but this doesn't really take into account all the other economic benefits. This was just purely the value of nitrogen and the value of the tonnage and the quality coming off of it. I did not take into account the shorter growing season, so we can have the ability to double crop, where yes, our variable costs would increase, more fertilizer, more seed, but definitely the fixed land cost would be averaged over the 2 crops. So some conclusions for objective 4, comparing the corn and rye systems: less tonnage in rye, increased protein compared to corn. The ADF, acid detergent fiber, and the total digestible nutrients were variable, half and half it seemed, and then the net return is equivalent only when the rye quality is higher, but not all those other confounding factors. So just to wrap up these overall conclusions, if I haven't said it enough, spring nitrogen rate is much more important than the pre-plant nitrogen. And something really interesting is that we found the total nitrogen requirement is about 2/3 that of the I guess now the previous recommended rates, because now these are the current, where the optimum rates now are less than 30 pounds, and then in the fall or in the pre-plant, and then 60 to 90 in the spring, in the very, very early spring. We also saw that there was an increased flexibility for N application in the late fall versus the early spring that can produce similar yields, so that's that increased flexibility for producers, with little differences in sources at the same N rate, and that may have just been a sign of, we had precipitation right afterwards, the temperatures were low enough, so those were only 2 of the years that were able to take that weather and field conditions that might be different depending on the year. And finally, the economic benefits of a higher forage quality if you're utilizing it for a forage crop with similar net return with that higher forage quality, and then also the double cropping opportunity, as well as the environmental benefits, this anecdotal information that I was able to observe, the water and the nitrogen uptake in the periods with the highest risk to leaching and nitrate removal out of the system, as well as it retrieves any residual in. So basically, whether you like it or not, hybrid rye will soak up everything. So something to be cognizant about if you're thinking about growing hybrid rye. But I think hopefully I have time for a few questions if there's any. and hopefully I can convinced you of my love of small grains and hybrid rye. Isn't it cool? So
Any questions? Yes, sir.
In your comparisons of corn silage and rye silage, did you look at palatability and how the cattle responded to that?
no. We only did quality factors such as protein, ADF, TDN. But yeah, definitely. I've learned that you could just keep going down this rabbit hole of things. But definitely, as far as palatability, we did take it at soft dough, so that may. I'm saying very conservatively soft dough. Sometimes it was even past that. So I would definitely the longer you wait, definitely the palatability would definitely decrease. So
Tara, I got two questions. One is you said your nitrogen response data was kind of a not a nice smooth line because you have pretty low R squareds. Were your previous crops kind of everything, or was it almost always after soybean, or?
almost always after soybean. There was up in Crookston, there was a couple of times it was after clover, so it wasn't always ideal, but definitely for the majority of the time after a legume.
And then the second question I had was, I was trying to get that from your graph, and maybe I missed it, but your relative yields, did it show that the northern part of the state typically had higher yields than the southern part, or was it vice versa?
That was all relative just because of between the site years, but generally, yes, the northern definitely had I mean, upwards of 120 bushels an acre, whereas the southern would maybe be at 100, 110. So definitely differences. That's why make it all relative so we can really extrapolate those differences.